we've seen that it is a relatively simple matter to calculate the number of moles of a substance that must be involved in a reaction according to the number of moles present of a different substance. But there are other quantities we can calculate. Looking at this diagram again, if we were to use the number of moles of a reactant to predict the number of moles of a particular product to expect, we could then use Avogadro's number to convert this into the number of molecules that value represents. This is because 1 mole is equal to Avogadro's number, regardless of the object or substance in question. 1 mole of water molecules and 1 mole of stars, while they represent incredibly different masses, still represent the same number of objects, and that number is always Avogadro's number, or 6.022 times 10 to the 23rd. For example, let's examine the combustion reaction involving propane. When hydrocarbons combust, they always generate carbon dioxide and water. So here is the balanced chemical equation for this reaction, complete with the correct stoichiometric coefficients. If 0.75 moles of propane were to combust, how many carbon dioxide molecules would be produced? Remember that first we must figure out how many moles of carbon dioxide are produced before we can convert that value into a number of molecules. We know we should get 3 carbon dioxide molecules for every molecule of propane, so using the stoichiometric factor, we can convert our moles of propane into moles of carbon dioxide. Once this conversion factor is in place, we can use another conversion factor to go from moles of carbon dioxide to the number of carbon dioxide molecules. This conversion factor will have Avogadro's number over 1 mole, because those two quantities are equivalent. Doing the math, we should get 1.4 times 10 to the 24 carbon dioxide molecules. Let's try one more for practice. According to the following reaction where ammonium sulfate and calcium hydroxide generate ammonia, calcium sulfate, and water, if 4 moles of calcium hydroxide react, how many ammonia molecules will be generated? Once again, multiplying by the correct stoichiometric factor, which we know from the balanced equation will be 2 to 1, and then multiplying by Avogadro's number, we should get 4.8 times 10 to the 24 ammonia molecules, a very large number indeed.